Hello, everyone, and welcome back to our final talk for today. And for this final talk, please welcome our next speaker, Konstantin Osipov, who is Director of Software Engineering at ScyllaDB. And today we will be talking about scaling Raft consensus algorithm. Hello, Konstantin. How are you?
Hi, I'm good, thanks. How are you?
I'm good too, and I'm glad to see you at our conference. So, you know, Konstantin, some time ago, after I read the famous Google paper about how they made Paxos live, I was always wondering about the gap between the ideas that are presented in, let's say, academic papers and the challenges that engineers face when they try to implement these ideas in practice. So I'm really excited to learn about what you're going to talk today, and hopefully there will be a lot of things that people can apply in practice when they will be implementing their own Raft implementation.
Yeah, and maybe you know that Raft paper was born as an answer, as a response to the complexities of Paxos. So today we'll see if Raft is any simpler.
Yeah. So I'm really excited to learn about that, and for everyone who is watching this talk, feel free to ask questions during the talk, and we'll be trying to answer them as we go through the slides. So shall we begin?
Okay, so thank you, and I'll be today I'll be talking about scaling Raft. Put differently, it's about applying Raft to circumstances of ScyllaDB, a distributed database I work for. And about myself, I've been involved in databases for quite a long time. MySQL, Tarantul, now ScyllaDB. And in Scylla, I'm working on distributed algorithms, so I know a thing or two about Paxos and Raft. And this talk, I'll begin by explaining what ScyllaDB is and what problem we are trying to solve, so that you can get the context in which we are going to apply Raft. Then I'll make a Raft introduction. So while I'm introducing Raft, I'll begin showing some of the complexities that arise in the context we are going to use it in. Then I'm going to talk about our extensions, what we did to actually make Raft scale, and I'll define scale by scaling to many nodes and scale to many groups. I'll define that, and then we'll have a chance to respond to your questions. So what is ScyllaDB? There are lots of databases out there, and there are NoSQL databases, relational databases. ScyllaDB is a distributed, large scale, so it can run many nodes and store lots of data, like hundreds of terabytes of data. Implementation of Cassandra. It's eventually consistent. Its main focus on low tail latency, so that you can put and get your queries quickly. You could look at it as a very powerful, and by powerful I mean extracting lots of performance from the hardware implementation of a NoSQL database. And before I talk about Raft, let me just describe the landscape of Scylla, what it means to be an eventually consistent database, how Scylla handles queries, and why we have the need to scale Raft. So Scylla is a distributed, highly partitioned database. By highly partitioned, I mean that pretty much every key has its own set of replicas, can have its own set of replicas. The way it happens is that Scylla does use a variant of consistent hashing, which means that every node that is present in the cluster, its value is like signature node ID is hashed, and we get a number which you throw on a numeric ring. And in order to determine which key belongs to which node, we also hash the key. We throw the hash to the ring, and we see the nearest hash of the node that's on the ring. Scylla calls hashes, these hashes tokens, and this ring is called the token ring. And the entire state of which nodes are out there, what tokens they own, is called token metadata. And when you perform a read query, you hash the key which you're going to read, you determine which node you're going to go to, and then select the record from that node, search on that node. When you do write, to ensure durability of the writes, you write to more than one node. And besides the primary replica, there is a secondary and possibly a tertiary replica. So in this picture, we have a replication factor of 3. So we have 3 replicas. And these replicas, secondary, tertiary replicas, they just the next tokens are owned by some nodes on the ring so that we can store the key on more than one node. One thing is why is this eventually consistent? The write succeeds as long as it can store the record at least at one node, and there is an eventual process that replicates the records to other nodes. But besides the information about the data, where the data is stored, there is metadata. There is information about the current token metadata, and that's also maintained using eventually consistent algorithms. So the metadata, what tokens are out there, what nodes are out there, what nodes are alive and dead, is spread through the ring. Every member of the ring, every cluster node has its own copy. And Scylla uses an epidemic, eventually consistent algorithm called gossip to just distribute that data. The idea is that as long as you have just one change at a time, a ring can be, every node in the ring can be either in the previous state where it knows about the previous state of the ring, or in the new state. So in order to address like even eventually consistency concerns in this situation, Scylla make sure that when there are topology change operations, there are sufficiently long timeouts to make sure that everybody in the cluster learns about the new node, that the data is being distributed to more than the replication factor. So if we have a ring that is like has 3 nodes and replication factor 3, and we added in the 4th node, that 4th node is going to get the writes while it's being added, so that we just make sure that the data is going to be replicated to it while the topology transition is in progress. And that ensures that the eventual consistency works. The only problem with that approach is that it's not always the case that you have just one operation happening at a time. Imagine you are trying to add a node to a ring, and there is a failure of some node, and you have to remove that node or somehow address that failure. So with serverless, we also have another issue, that there is a Kubernetes operator now operating on the ring, and the Kubernetes operator cannot, it's not a human, it cannot always ensure that the ring is in fully transitioned from the previous state. And this is why another reason why we need a strongly consistent algorithm. So right now our documentation says, like, just don't add more than one node at a time. Don't add nodes when some node is down. With serverless, we cannot always guarantee it, and we would like to use a strongly consistent algorithm to maintain topology information. And then the final bit, the schema information. The schema information is also eventually consistent, is also distributed through a form of gossip. And that means that the replicating schema statements, it uses its own write path, and every member of the cluster is prepared to work with a slightly outdated schema. The way it works is that if you send the query to a node, and that node doesn't have the version of the schema that the client has, it just fetches that version from the nearest node, or if it has a more new version, it can convert data to the version of the client, so that the schema of the record is either upgraded or downgraded on demand to match the schema of the client. And this information is also eventually consistent. So it's allowed to make schema changes. You shouldn't do it, but there is no prevention again, schema changes happening on in a cluster that's split, that is experiencing split branch situation. So in theory, you could add a column to a table in one part of the cluster and add another column in another part of the cluster, and later this information is reconciled. And this is not always, of course, successful, because not every schema change can be eventually reconciled into a common schema like here. And this also leads to some funny situation where we would like to apply strong consistency. So to sum up, there are strong needs for strong consistency in Scylla. We would like to use a strongly consistent algorithm for reliable and concurrent topology changes, to linearize cluster-wide schema changes, and eventually we would like to get strongly consistent data so that we can use it. So welcome Raft, an algorithm we decided to adopt to implement these features. And the rest of my talk, I'm going to structure around describing what Raft is, and then showing the limitations of Raft that we had to overcome and how we overcame it in Scylla.
Konstantin, if I can interrupt you, there is one question already. So the question is from Vitaly Isaev, and he asks to clarify, is it possible to add nodes to Scylla cluster even if some of its members are temporarily or permanently down?
You shouldn't do it. So the answer is threefold. First is the best practice is to first remove the node that is down from the cluster, and then begin adding a new node, so that you don't have, when you remove a node from the cluster, you rebalance the data in the cluster, so that the data from the dead node, so the dead node is not accounted as alive, and basically we redistribute the data to ensure the same replication factor. And then it's also about repair. So in Scylla, there is, like in Cassandra, there is a repair process that runs in the background, and that it reconciles or eventually propagates the data to all of the replicas. So whenever you have a topology change, it's the best practice to first run a repair, so that all of the replicas are up to date and all the data is replicated to all of the nodes. That's the first part. Then there is a disaster recovery scenario in Scylla, when you have to do what you have to do. And there is a special switch for that, you are ready to accept some even eventual inconsistencies and lose some data. And there is a switch called mark nodes dead that allows you to do to add a node in presence of a temporarily down node. But the results of this is that you can get outdated data in the cluster for some of the keys. All right,
thank you.
so let me go on and talk a little bit about Raft and how we use it. So first, what is Raft? It's a protocol for state machine replication. These words, they might not sound familiar, and to understand what it means, imagine you wanted to perform some process in a reliable manner in a distributed environment. So you have some agents, every agent, you want them, like state machines, you want them to transition from into the same state eventually. And in order to do that, you could just make sure that every state machine in this distributed cluster applies changes in the same order. So if you make sure that the state machines apply the same changes and they do that in the same order, you can these are deterministic state machines, you can guarantee that they transition to the same state. So based on that idea, Raft uses make sure that, so Raft exploits that idea. And in order to do it, it has three components. First, there is, of course, the state machines, and there is an independent state machine on every node. And second, there is the log. So before Raft, every node has a persistent log, and before a command is applied to the state machine, it's recorded in the log. As soon as it is recorded in the log on the majority of the replicas, on the majority of participants, we can make sure that this command is not lost, and we can apply it to the state machine. And third, there is this part that's called the consensus module that does the log replication, does leader election in case the Raft is a leader-based protocol, so there is only one member of the cluster that accepts changes from the client initially, and that makes sure that the changes, like it implements the protocol, the logic of the protocol, elects the new leader, performs configuration changes, replicates the log, instructs the state machines to apply entries which are committed in the logs that are distributed on the majority. Also, there are situations when you have to overwrite the log once there is a leader change, and it makes a decision to do that, and so on. So that's the consensus module. So Raft consists of 3 parts. And the idea of Raft, it's built on the majority principle. And maybe you are familiar that the whole idea of this quorum of majority is that as long as you have at least one member that is aware of the latest state, you can preserve that state sort of for future generations. So if you have 2 nodes out of 3 that have the latest state, even and you require that to commit any new change, the majority is being used, and there is this majority intersection rule. So whatever 2 nodes out of 3 you pick, A, B, C, you pick A, C, you pick B, C, you pick A, B, there is going to be a quorum intersection. Some of the nodes from the nodes you picked is going to know the latest state. So that's the principle of the majority, and Raft exploits it to make sure that the algorithm is consistent and live if you have a majority of nodes live in the cluster. So 2 out of 3, 3 out of 5, 4 out of 7, and so on. So I mentioned that Raft is leader-based. What it means? What does it mean? It means that there are 2 modes of operation. First is a normal mode, when the leader is responsible for committing all entries to the cluster. To the cluster. And then there is this disaster recovery mode when the leader is dead and we need to elect a new leader. So for normal operation, most of the nodes are passive. They listen to commands from the leader, they apply these commands, and they do nothing else. They respond to the leader and so on. So when the leader is dead, there is this election mode when every follower can become a candidate and promote itself to a leader. And this creates a completely different situation that we are going to look at, the leader election situation. So first, let's consider that situation from a detection point of view. How are followers detecting a leader failure? One of the leader's responsibilities is to regularly ping the followers. So every 100 milliseconds, if there is not traffic in the cluster, if there is a traffic, there are some entries that are being added, it's not necessary, but if the cluster is idle, the leader is responsible for sending a special empty append entries request, empty ping request to the followers. And if followers don't get more than, I say, 10 pings in a row, they decide that the leader is dead, and they promote themselves to candidate state. So the full state machine, just let me scroll real quick to forward, jumping ahead. That would be the full state machine of a node. So it starts as a follower, and if it times out and it starts a new election, it promotes itself to a candidate state, and then it can win an election. We will talk a bit in a second, in a bit, what it means to win an election. Then it can become a leader, and there can be only one leader in the cluster during the same that can win in a single election. So that's the major principle of Raft, that a single round of elections can yield only one leader. Of course, if you could yield 2 leaders, you could not get consistency. But you could have multiple elections running at the same time. Let's look at that. Let me go back to my slide. Before we move on and we discuss elections, please acknowledge one moment that the bigger is the timeout before a follower becomes a candidate, the more patient it is, the lower is the liveness of the algorithm, the lower is the availability of the cluster in case of a leader failure. So if you have to wait, you of course cannot commit new entries, and the leader might be dead, but you're still waiting because the leader might be alive, and so on. So how do elections happen? Imagine there is this election timeout, and nodes at some point promote themselves to candidate state and begin soliciting votes from other nodes. It might happen that more than one node does it at roughly the same time. In this slide, you can see that node S1, its election timeout is triggered, and it starts sending the packets to nodes S5, S4, S3, and S2, the vote for me packets. And if node S1 has a sufficiently up-to-date logs, S5, S4, and S3 are going to vote for it, and we are going to get a new leader, and we are going to be happy. But quickly afterwards, node S2 is becoming a candidate as well. Of course, it's not aware that S1 is already a candidate. It's a distributed system. So it also might happen that S2 sends its vote requests to other nodes and gets some of the votes, but not enough, not the majority to become a leader. And that's a situation that's called split votes, and it's a major liveness concern in Raft. And I'm going to talk how we address that concern, because we are using Raft for very large clusters. Typically, typically you don't have a lot of split votes, and if you have a split vote, like in a cluster of like just 5 nodes, and like in this diagram, you just retry the election after a timeout. And so like before we look at the problem more closely, like let's imagine the nice case. We have like 5 nodes in the cluster. There is a leader failure, so the nodes E, D, B, and C, they wait for some time for the election timeout, and they choose a random sleep interval, and they that is proportional to the election timeout. They sleep a bit more, and then they become candidates, and one of them, in this case E, is going to win the election. So as long as the network round trip time is much shorter than a timeout time, E is very likely to win the election before D becomes a candidate. But what happens if we have like many nodes in the cluster? In this case, as long as we scale our election like threshold, as long as we scale the randomized timeout proportionally to the election timeout, it is possible that 2 nodes become candidates at the same time, or 3 nodes. And if you have like 1,000 node cluster, you can have 10 nodes becoming candidates. And of course, nobody's going to get 500 votes out of these 10 nodes, like out 500 of 1,000 node cluster. That's necessary to win. So we encountered this problem, and as long as we use Raft for schema and topology group in Raft would involve every node in the cluster, so potentially hundreds and even thousands of nodes. We had to solve that problem. We spent some time looking for solutions. So one of the solutions we considered, and we emulated the sort of our algorithms. We ran them through a simulation in slow networks, in networks that lose packets, with large number of nodes, with small number of nodes, to see if nothing, if the main case is not impacted. So we try to use Gaussian distribution for the election timeout, so that like most of the nodes would trigger the timeout at the end of the range. So let me show it here. Just a second. Here at the end of the range, and this worked quite nice, like till the cluster size got above 300 or 400 nodes. And there were also issues when you have some asymmetric failures. So some of the nodes, basically, if the cluster is, in addition to be very large, is also struggling with the network, then it also didn't show good results. So then we started to think, maybe we could exchange information about like who won the election the last time to only like run the next election among the winners. We started to apply some complex algorithms, but the solution actually turned out to be quite simple. And that was, instead of using normal distribution, Gaussian distribution, retries, 2 total elections. We just needed to scale the election timeout proportionally to the cluster size, not proportionally to the election timeout itself. Turns out that it doesn't impact liveness in any way. So most of the times, there is a node that's quickly becoming a candidate, even if you have like thousands of nodes. So it's just, but if that doesn't happen, your election can run for, instead of like typically running for a second, nodes can wait for 10 seconds, 100 seconds, even very large cluster, before they even trigger that they become a candidate. But because there are so many nodes, it's very likely that some of them, there will be a sufficient amount of nodes that will try to become candidates in this environment, and the liveness will be preserved. So the other problem we had to solve is the whole detection performance, like failure detection performance. Imagine I mentioned that we plan to use Raft for schema changes, for topology changes, and for data. And before that, I said that in Scylla, pretty much every key could have its own set of replicas. So if you imagine a cluster, say, of 100 nodes, and the replication factor of 3, that gives you a huge combinatorial like permutation number for possible replicas, and therefore for possible groups in such a cluster. And every group in the cluster has to have a leader and has to ping the followers. So we get every second, every 100 milliseconds, we get the number of pings that's squarely proportional to the number of groups, and the number of groups can be much larger than the number of the nodes. So we had to do a shared failure detection, and a shared failure detection idea is that every node pings every other node, but this information is shared between many Raft groups on that node, so that they don't do their own pings. And by the way, if you look at some other implementations that had the same problem, TiDB, etcd, CockroachDB, they don't do it. They don't share a failure detection. They multiplex pings from many groups into like very large packets, so that they save a bit on the network traffic, but they don't save on the computational complexity of the problem, because they multiplex it and deliver the ping to every other group. So, but there was a catch with our approach, and the catch was that Raft liveness is connected to Raft configuration. I haven't been speaking yet about how Raft manages to change configuration. And the configuration is like, who are the members of the cluster? And when you add a node or remove a node, in Raft it is possible to add a bunch of nodes or remove a bunch of nodes or just replace a bunch of nodes. That information changes. So what could happen is that when you remove a leader of the cluster, and the failure detection is shared, that leader is logically removed from the cluster, but physically it's alive. It's responding to pings. So every node in that group that has a leader removed would still think that that leader is alive and would not nominate itself as a candidate. And that was a problem, of course. And so the way we addressed that problem is by adding two things. First, we added entry forwarding. We made sure that it's not necessary for a follower it's not necessary for the client to forward to connect to the leader, to send its entry to the cluster, to basically make a write or a read. And it can connect to any node, and the node then sort of works on behalf of the client. Of course, it could do that if it knows the leader, but we just mentioned that in the situation above, the leader could be removed, and these nodes B, C, D, and E, they could be in a state that they believe that they know the leader, or they even don't have the current leader set. They don't know the current leader, so they wouldn't know where to forward it. So that only solved half of the problem. The other half was to actually solve this uncertainty when you don't know the leader, and new leader is not contacting you. So maybe you're supposed to become a leader, and that would invert the problem altogether. So every node would still need to ping the leader. So in Raft, leaders ping followers. Followers are passive. And if we want to know at every point in time in every follower who is the current leader, we have to do the pings on the follower, which we would not want to do. So, but because we added support for forwarding, we sort of inverted the problem, and we could only do the pings on demand. So what we did is we added follower pings, but we perform them only when there is this uncertainty state. We have some work on the follower that we need to do, but the follower is not aware who the current leader is. And in that case, the leader does the inverse pings. So we share a failure detector, and we add a new feature to Raft that's called like inverse pinging to support the situation. So, and if there is a traffic in the cluster, of course, and there is a leader in the cluster, then followers learn about who the current leader is, because the current leader will send append entries messages to the followers. So that's the second extension we did. Finally, I'd like to talk about a few extensions related to configuration changes. Before that, let me briefly explain how configuration changes work in the Raft itself. Raft uses a very neat idea of pushing the configuration changes through the very same replicated log that holds the actual data entries, changes to the state machine. So the log is used for two purposes. One is to store entries to the client state machine, to the user state machine. And two is to store the entries for the consensus module itself. So the consensus module also has some persistent state that it could store in a or you could at least sort of present it that way, so that it can store some part of its persistent state in the log. And with that, configuration changes in Raft are actually quite simple. There are two configuration changes algorithms described in a Raft paper and in the community. One is simple changes, and here on that slide I demonstrate how they work. So basically, as soon as you want to change, add a node or remove a node, you add an entry to the log, and every member of the cluster, as soon as it gets that entry, it doesn't matter whether it is committed or not yet, it applies it, and it assumes that the cluster has transitioned to the new configuration. If there is a leader change and the log is overwritten, then there is going to be another entry, and this configuration will be reverted or overwritten. And this works only if you add or remove a single node. If you do add or remove more than one node, it's been proven that this algorithm doesn't work. So there is a more complex algorithm that's called joint configuration or joint consensus, and it splits the problem of configuration changes into two. One is entering this joint configuration. So when you want to change and you say add or remove a few nodes, you basically instruct the entire cluster to apply a configuration that combines the old and the new. So every decision in the cluster has to be valid in both cases, in cases of the old quorum and the new quorum. So imagine you have nodes A, B, C, and you add node E. So you have to have a majority in the cluster ABC to commit any entry, and you have to have the majority in cluster ABCE to commit a new entry. So that's called the joint mode. As soon as the joint entry is committed, which means that the joint configuration is adopted on the majority of the nodes in the cluster, another entry is added to the log that transitions out of the old configuration, and that instructs every member of the cluster to adopt like the final configuration already. And this process already is safe even for transitions that replace the entire content of the cluster. It's been proven that it is safe. They are safe, but are they live? Is it possible to get into a situation when some disaster, some crash during a transition could lead to to a cluster being stuck in a lack of quorum and a lack of consensus and cannot like move forward or move back to the previous configuration, elect a new leader and so on. Let's look at that. And by the way, before I transition to that, generally followers in Raft are not configuration aware. They don't need to consult with the configuration because they're passive. So the most of the work is on the leader. So, but let's consider a very small, actually tiny cluster that's that only contains 2 nodes and that uses either joint or non-joint configuration, doesn't matter. Imagine you add a node B to a cluster that used to contain just node A. Then probably you begin rebalancing your data, your distributed database, you probably begin moving some data to the node B. And imagine you crash in the middle, you run out of space, or there's a configuration error, or there is a runtime error, and B just crashes. The entire cluster becomes essentially stuck. It cannot move back. It cannot move back to configuration A because AB is already committed, and it cannot finish the transition because B is dead, and A is lacking the quorum to commit any other entry. And in order to avoid that condition, Raft, the standard Raft, introduces a mode that's called that's called non-support for non-voting members. When B is actually part of the Raft configuration, but does not vote for leaders. So if B dies in the middle, then A can commit a configuration that actually removes B, and we can retry A and B under a new incarnation after fixing the problem and so on. So that's also support that we had to add. And another thing another extension that we added is I'm building up to something. Just wait, because there is an interesting problem that's we just need these ingredients to describe that problem. So another thing that we added is a support for non-voting members, for pre-voting. I'm sorry. So the standard diagram, state transition diagram in Raft is simple. It's every node can be either a follower, a candidate, or a leader. It turned out that there is a liveness problem with that approach. So it is possible that followers that become candidates all the time can disrupt an existing cluster with necessary elections and never actually win these elections. So one case when this is necessary is when you have say, imagine you have a configuration of S2, S1, S2, S3, and S4. And you commit, sorry, S1, S2, and S3. And this is a screenshot from the Raft paper from the PhD that went into, that's widely used to implement Raft. And you add a node S4, and I'm sorry, you remove, you have a cluster S1, S2, S3, S4, you remove S1, S4 becomes the leader, but not everybody yet knows that S1 used to be the leader. Not everybody knows that S1 is removed, and S1 doesn't know that it was removed. That's the most important thing. So in that case, S1 will try to become a leader, and it will send the election request to other nodes, and the cluster will continuously try to elect S1, but S1 is never going to get the new configuration because it's not part of it. This entry is just not going to be sent to S1. So that's to protect the cluster from disruption during configuration changes. The cluster implements pre-voting when the follower, before it actually becomes a candidate. It has this intermediate state here on that verge when it requests the cluster to confirm that it could actually win. If it can't win, it will not even try to become a candidate, will not try to run an election, and will not disrupt the cluster. So that's support for pre-voting. And here comes the interesting part. The original paper, even though it's does introduce pre-voting, like in this chapter is 432 disruptive leaders, also says that despite pre-voting, it is possible that there is a disruption in the cluster anyway, And there is there is a necessity for an extra rule that's called the sticky leadership rule, and it's described on this slide, that instructs the followers to not vote in an election if they heard from a valid leader. And this rule is actually very painful to us because in our case, the leader doesn't actively ping the candidates. Remember, we share the failure detector. So there are no pings in the specific groups. There are pings like across the physical nodes in the cluster. So we share the failure detection information. So we couldn't support that rule in our environment. Turned out that if you have a joint configuration support and you don't support simple configuration changes, you have pre-voting support, that the sticky leadership rule is completely redundant. And this is also part of our implementation. We don't implement sticky leadership support. With that, I'd like to summarize. Scylla Raft implements a number of important extensions which we had to do to support very large clusters, to support shared failure detection, and to support multi-Raft, or at least what we call multi-Raft. Raft support in, how many times did I say support today? Raft in many independent groups that share most of its state. And we removed some of the core features of Raft, simple configuration changes and sticky leadership, which we believe actually made our implementation more simple and more robust. Thank you. And if you have any questions, I'd be happy to answer them.
So, Konstantin, we do not have any questions in the chat so far, but I do have a few questions. So probably we'll just discuss them and see if people have more. So
Sure.
one thing that I was wondering. So you mentioned that you have implemented non-voting members, right? And on the other hand, use, as I understand, if you have 1,000 node cluster, then in a stable state, all nodes in the cluster are voting members, right?
Voters. Yes.
Yeah.
Yes.
So
we had a debate around this. It's a great question. Thank you. I didn't mention it. And yes, some of the implementations they suggest that if you have a very large cluster, you only enable few nodes as voters. We consider that, and in Scylla, we believe in homogeneity. So we believe that every node should be alike. It should be simple to add or remove nodes. There should be no special nodes in the cluster. We spent a lot of time in removing the concept of seed nodes from Scylla. These are the special nodes which should be alive. So at this point, at least, we decided to make sure that our implementation is efficient enough so that we can support voters in, like every node can be a voter, rather than just select a few nodes as voters. But we can always revert, like having non-voter support would allow us to do it.
Mm-hmm. I see. Yes, and now we do have one question from our audience. This one is from Mirza Aliyev. And he's asking this thing. So Raft algorithm is based on inequality that election timeout must be an order of magnitude less than mean time between failures. And in your approach, when you scale up the cluster, it seems that you can end up in a situation when mean time between the failures will be close to the election timeout. So does it bring any inconsistencies or problems with your implementation?
Two things. And by the way, if you ask me, can I prove what I say? And I'll be frank, I can't. And it's an interesting problem in itself, because if you go and you check for TLA plus for Raft, you'll see that only the basics of Raft are covered with TLA plus. Joint consensus configuration changes, pre-vote, nothing beyond replicating, and I believe not even leader election. I don't remember whether simple leader. Yes, I think replication and leader election are covered by TLA plus, but configuration changes and everything beyond that is not. So we don't have a strict proof of safety and liveness of every extension that we've just discussed. So going back to your question, there is, I believe, the liveness issue that is stemming from, so in order for, it's not the safety part of the algorithm that's going to break, it's the liveness part. And we observe that if your election timeout is close to mean time between failures, you are essentially going to be stuck with elections. You're never going to elect a leader. We could observe that. Does our algorithm sort of fix that or enforce that? I believe it rather fixes that, because we don't increase the election timeout. We increase the part. The election timeout is how many pings you wait until you decide to become a candidate. We don't increase that. We increase the randomized part that comes after the election timeout. So imagine you have to do 10 ticks, wait for 10 ticks, and then you could wait for another random number before you become a candidate. So what is this random number? In vanilla Raft, it got to be proportional to the election timeout. In our case, it's proportional to the cluster size. And the numbers we got are pretty good, like the simulation numbers, the liveness numbers. And of course, if you go back to testing, we cannot imagine we run TLA plus for the whole thing. Even if we could write it, running just the simple TLA plus for the basic Raft takes hours and hours. So we just use randomized testing, nemesis testing, simulation testing to cover as many cases as possible. We found quite a few bugs, but didn't find stuck elections or safety issues with our implementation. So that's, at least that makes me believe that this kind of works.
Mm-hmm. Yes, and you know, I think it also matches my understanding, because Raft is expected to be safe in arbitrary message delays, right? And I think we can simulate or just imagine that this increased election timeout that is increased arbitrarily can be simulated, but just delaying the message in the network, and so the Raft still should work correctly in this case. So yeah, I agree that the safety property should not be a concern in this case.
Yeah, thank you. Actually, that's even it's a better answer than I could give. Thanks.
Yeah, we yet have no questions so far, but I do have another question. So you mentioned the pre-voting phase to actually allow the cluster to be live, right? Because in certain network configurations, there may be cases when without pre-voting, the cluster can be stuck. I was wondering, did you also implement the check quorum thing? Because this is one of the configurations, for example, in etcd, and the second improvement is also required for, let's say, strict protocol liveness.
You would have to tell me more, but I can say one thing about etcd. If you go back to the cloud, the whole pre-voting story became big after the Cloudflare failure in 2020. And I don't know if you read the postmortem. It's actually quite an interesting failure and quite an interesting postmortem. The culprit was etcd that was running on a previous version that was not running with pre-voting enabled. So we only started implementing Raft when we read that postmortem, so pre-voting became a big thing for us. And if you also remember that story, like there was this tweet by Heidi Howard, like, hey, Raft is broken because look at what happened to Cloudflare that uses Raft and so on. And this is why we just, Raft is not broken, but pre-voting is essentially not an optional part. So that's one part of the question. And I believe when you are asking about check quorum, you probably mean read barriers and reading on followers. So yes, we do support reads on followers. That comes hand in hand with entry forwarding, so followers can send read barriers to the leader, and they can forward entries to the leader. We did it together.
I see. Yeah, actually, I remember that post, and there was a follow-up from, I think, Heidi and some other person where they described that, vanilla Raft is basically there are situations when it's not live, but then there are these two improvements that are, I don't remember if they fully covered by the PhD thesis or the follow-up papers, but yeah, once you have these two things,
it's amazing. Yeah, whether or not they are covered. So, and it's also a story, I think. I've been when I started, I became familiar with Raft when it just came out, but I wasn't really looking into all of the details. And when I started implementing it, I did a part of archaeology. So I looked at the history of the Raft mailing list, at how the paper was developed and extended, at how people were sending sort of issues that they found with the initial implementation. And I believe that pre-voting and sticky leadership rule was sort of a later addition. And I believe even joint configuration was a later addition as well. So these are the major parts of Raft. Like without them, I think things would break quite badly. And if you look at these parts, and you look at the algorithm as a whole with these parts added, you could probably come up with something much simpler. And this is why I say that first, Raft is not easy, because the whole story of Raft was this Raft study. The PhD contains a major chunk where they survey students, they present multi-paxes to them, they present Raft to them, then they ask questions, and they sort of statistically prove that students are able to answer questions better after the same time spent with Raft and the same time spent with Paxes. So, but the tricky part is that at that point, the algorithm didn't contain like sticky leadership, pre-voting, and all of these extensions. So it wouldn't be fair. So Raft is not simple. That's the short part. And the other part is, just let me go back to this slide. I think what we did by adding and removing some of the features could take Raft to sort of next level, and it is making it more complete. Unfortunately, the discussion around this algorithm is not very hot now. So we sent our sort of changes to the mailing list, didn't get a lot of replies. Raft is becoming very popular. There are many canonical implementations, but I don't see anyone in like universities try to come up with something next. So there is, of course, there are some transactional algorithms, but coming up with a simpler Raft is not being worked on.
Yeah, I agree. We have two more questions. One is a follow-up question from Mirza. So he's asking if Scylla uses gossip as a transport protocol, and if so, does the gossip suspicion timeout bound in any way to the election timeout?
No, it's not. Thank you for that question. Luckily, it's not, and it would break miserably if it was. So the big problem with any gossip-based decision making is that it's so slow. If you are basing your decisions on like election, on any kind of timeouts, like adding a node to Scylla before Raft, it could take 30 seconds, 60 seconds, just to wait for gossip to settle. With Raft, it takes a sub-second time. So no, it's not bound. And with Raft, of course, not. It's not because Raft timeout is so much better, but because with Raft we are relying on normal operation most of the time. And if we would bind them, so I mentioned that gossip, even gossip view of the topology is not the same as Raft's view of the topology. That's also an issue. We cannot. Gossip cannot be a source of truth for Raft. Let me put it this way, because Raft got to rely on its own consistent information about the current configuration.
Thank you. And the next question from Andrei Satarin. He's asking if Scylla uses a single Raft group for the whole cluster to store the schema, basically the schema configuration and schema changes.
Yeah, that's right. And that's why we had to scale it. Yeah.
Mm-hmm. Thank you. So you mentioned that you are using Raft to store the schema changes. Any plans to also use Raft to replicate the data itself?
Yeah, and we are working on that. It involves a lot of changes, but so when we discuss replication, it's not just about replication, it's about how we partition data. So right now Scylla uses hash partitioning, and we would like to have a configurable partitioning, which we call tablet partitioning. The deficiency of hash partitioning is it's uniform. You cannot manage it for tiny tables. So even tiny tables have been spread across many nodes, which is not optimal. So we are looking into changing that. We are of course looking into using Raft to replicate changes to them, but it also means that we have to look at our commit log implementation to make. Essentially, we have multi-Raft, so we have to multiplex logical Raft commit logs over some physical commit logs that we store on disk. So it's a lot of work, and we are doing it.
Mm-hmm. Yeah, I agree. And probably one of the interesting things about Raft log that at least kind of made me think about how I would implement it is that actually once you append log entries to the Raft log, right, and until they are not committed, you may truncate it because, essentially the Raft state machine can truncate any entries that are beyond the commit point. And so your log implementation should be efficient to support such scenarios, even though are maybe quite rare.
You're right. However, I was also involved a bit. Here I'm taking off my Scylla hat and taking on my Tarantul hat. So in Tarantul, there is no support for truncation, yet Tarantul does implement Raft, and it just has a logical truncation where it puts a special entry into the log saying, hey, and now, by the way, all of these entries up to that back in the history are dead. Don't use them. So there is a part of a magic during recovery. So when you initially start and you look at the log, you have to scan back. But otherwise, you don't. My point is that you don't need to physically truncate. So, but you're right. You're totally right. You have to support truncation.
Yeah. All right. So we don't have more questions, and so we have only 2 minutes left. So probably we can thank everyone who watched your talk. Thank you, Konstantin. It was really educational and interesting. And I invite everyone to join our discussion group in Zoom. I believe the link will be in the chat soon. And see you there. And thank you again, Konstantin.
Thank you. Thank you very much. Bye-bye.